So, you have a very dedicated team with you today. As it happens, I've just discovered that our speakers for today, Michela and Alessandra, both have the flu like me. So we're all here sick to talk to you today, but because it's all digital, it doesn't really matter. There is no infection risk. We're going to try our best to get through things without too much coughing and spluttering. Alessandra will join us in just a moment. She's just experiencing some minor technical difficulties, but the show will go on regardless of what happens there. She will maybe just present without her camera, or maybe with her camera. We will see what happens with that. So a big welcome back to the Resources Conservation and Recycling webinar program for 2025. This is the first issue of the program for this year. My name is Mitchell Jones. I'm the Outreach Editor at Resources Conservation and Recycling. It's an absolute pleasure to have you all with us again in the new year. I'm your host for today. A few brief notes on the program before we kick things off. So this is the English language version of the Resources Conservation and Recycling webinar program. We run it every second Thursday at 10 o'clock a.m. Pacific time. We also have a Chinese language version of the program. If you're interested in that, be sure to check that out. Now, this program that we run, our webinar program, it's in direct alignment with the scope of the journal. So you can expect to find a balanced program here that represents all elements of the journal scope equally. We have a broad range of topics in all of our webinars. The only thing that we do emphasize is audience accessibility. So we do ask our presenters to, where possible, minimize the use of jargon and field or topic-specific terminology and provide some basic background information, some fundamentals on their research area so that people that may be working perhaps in an adjacent research area or may be interested in their topic but not an expert can really learn something about the fundamentals and have some context and background information for the study that they're about to experience, or the study that they're about to be told about. Now, apart from the accessibility, we do need people to register for this program in order to use the Zoom environment, which is where we are now. So if you don't want to register, you can actually watch the program live on YouTube, which I will talk about in just a moment. But if you're interested in the Q&A and the full experience, you do need to register. The links for the registration you can find in the journal newsletter, which is circulated at the end of each month. You can also find those links on the journal social media pages. So the official page for Resources Conservation and Recycling on Facebook, on LinkedIn, and on X. You can also find the links on the Elsevier Journal homepage. So if you visit the Resources Conservation and Recycling homepage and you go to the About tab and then visit the webinar calendar, you will find the links for the upcoming events there. You will also find a full list of all of our previous speakers and their archived webinars. Now, the archived webinars are on YouTube. As I said, you can also view the live stream on YouTube. youtube.com/@RCR Journal. Go to that link. You'll find all of the old webinars there, plus a live stream of the latest ones. The final point is we very much appreciate your feedback. We want this program to be everything that it can be, something that you really want to watch and get something useful out of. As a result of that, at the end of every single webinar, we do collect surveys. You are encouraged, and we do greatly appreciate if you take the time. It's just 8 questions, maybe 60 seconds to fill in. We do have a survey that will open when you close Zoom, where you will have the opportunity to provide your feedback, criticisms, comments, suggestions for improvements, praise, whatever it may be on the program. We do actively review them, and we do seek to implement changes based on your feedback to try to create a program that you really want to attend and get something out of. Right, so I will switch now to the formal program for today. That is, I'm now going to introduce the program officially and our speakers. So, the event program, we have just had the welcome address. I'm going to provide a short introduction to the journal, then going to introduce our speakers for today, followed by some brief notes on the webinar etiquette/administration practices of our webinar program for those people that are new to the program, perhaps. We're then going to have an approximately 20-minute presentation from our speakers. Now, of course, if they go a bit over or under, that's no problem at all. We're very flexible with time, but we've scheduled approximately 20 minutes. We then have scheduled 10 minutes of question time, but we'll endeavor to answer any questions that you happen to have. So if you have questions, feel free to ask them. We will be sure to answer them. Finally, we will have some information on the next event and, of course, the closing remarks. So the journal, hopefully everyone is familiar with the journal Resources Conservation and Recycling. If you're not, it's an Elsevier journal. And I always like to say that our research interests are very clear from the name. Resources, conservation, and recycling. Those are our research interests. We have here some specific points that a little bit narrower scope. So systems-wide strategies, technological, economic, institutional, and policy focus, resource management practices, conservation, recycling, and resource substitution, resource productivity improvement, restructuring of production and consumption profiles, and transformation of industry. If you have any top-notch research in those areas, we would love to see it published in Resources Conservation and Recycling. So some admin notes for today. If all communication could please be in English, this is just so that we have a bridging language that everybody can understand. We also have closed captions available and running today, both in Zoom and also in the YouTube recording. So, for example, if you're somebody that perhaps likes to watch your videos on mute on the train or something like that, you have your captions there, you just need to enable them. Or perhaps if your English is not your first language and you might benefit from some captions to aid your comprehension, they are there. So feel very free to use them if you may find some value in them. We love questions, so feel very free to post any questions that you may have in the Q&A over the course of the presentation. If you wish to ask your question directly rather than via text, if you want to talk with audio or video to our speakers, we also have the capability to facilitate that for you. All you need to do is indicate that you would like to talk using the raised hand reaction, and we'll be sure to invite you onto the floor to speak with our presenters. So that brings me to our presenters. We're very fortunate to have today with us our two presenters, the first of which I will now introduce, Alessandra CESARO from the University of Naples, Federico II. Well, and I'll introduce her and then we'll talk about what the topic is. So Alessandra CESARO is Associate Professor in Sanitary and Environmental Engineering at the University of Naples, Federico II. Her research interests focus on the advanced anaerobic processing of organic residues, as well as the sustainable recovery of valuable metals and rare earth elements from waste electrical and electronic equipment. She has co-authored around 100 refereed publications in ISI, journals, books, and conference proceedings. The Scopus database entered on the 9th of September 2024 reads 65 publications, an H-index of 24, and 2,082 citations. Thank you so much for being with us today, Alessandra. Pleasure to have you. Alessandra is joined by her colleague, or her co-author rather, Michela GALLO from the University of Genoa. I should say at this point that they will be presenting to us on the topic of WEEE, sustainable recovery in a life cycle perspective. Michela Gallo is Associate Professor in Sanitary and Environmental Engineering at the University of Genoa. Current research activities include life cycle assessment and circular economy, greenhouse gas emissions reduction activities. She is also director of CESISP, which is an inter-university center for the development of product sustainability, and of the Titus Institute, and a university spin-off company. She's a delegate of the University of Genoa to the UN Conference of the Parties on Climate Change, and is also author of approximately 70 international and national publications, books, and proceedings. What a pleasure it is to have you both with us today, and so wonderful that we can see you now, Alessandra, that your face is again not a green blob anymore. That's fantastic. Okay, so I will now hand the floor over to our speakers. Thank you so much.
Thank you, Mitch, very much. Thank you for the kind introduction, and thank you also for inviting us to share our research with you. I will share my screen. Okay. Can you see it?
Yes, very nice.
In full screen mode, right?
At the moment, we see the windowed version. Now it is full screen. Very nice.
Okay, thank you. So, our work, as Mitch mentioned, focus on on waste electrical and electronic equipment, and in particular on its sustainable recovery. But why focusing on this waste stream? Well, first of all, because it is the fastest growing waste stream on a global scale. In 2002, only was estimated that in only 12 years, the amount of this waste almost doubled. And this is, of course, due to the technological evolution, the progress in electronic and electric fields, but also due to the increased consumption of this kind of devices, due to their short lifespan, as well as somehow to the poor options in repairing. Another point of interest of this kind of waste is for sure its composition. Of course, the composition of waste varies depending on the specific device, on the waste electric and electronic device. But generally speaking, we can say that it is mostly composed of metals. This means base metals like aluminium, cadmium, copper, that usually make the largest components of waste. But also precious metals such as gold, silver, platinum, and even more interestingly, in this waste we can find rare earth elements, which, as we know very well, are very valuable elements at high risk of supply. So, usually, when the waste is properly collected, is destined to recycling, but usually a mechanical pretreatment is performed. The mechanical pretreatment of waste before the let's say specific recycling plays a key role, because via a sequence of mechanical steps such as shredding, sieving, electrostatic or magnetic separation, it is possible to separate the relevant components such as aluminium, copper, or the plastics, and then send this selected material to the ad hoc recycling processes. Now, although these mechanical pretreatments works very well for, let's say, base metals, so the ones that, as I said, made the largest part of the waste, it is less effective for precious and metals and rare earth elements. And several studies has shown how these valuable components tend to concentrate in the dust that typically originates during the shredding phase of the mechanical pretreatments. And here you can see how you can see better now that cerium, europium, lanthanum, for example, are mainly present in the dust, in this so-called wish-shredding dust, rather than in the grains selected as output of the mechanical pretreatment. So how was the research idea? We decided to focus on this wish-shredding dust because although they can be considered really a valuable urban mine in terms of especially of precious metals and rare earth elements, they are currently disposed of in landfill. So we propose in our research an hydrometallurgical approach to divert this dust from landfill and recover the critical and valuable materials to bring them back in the manufacturing chain. Of course, the one of electric and electronic devices, but not only this one, because, for instance, rare earth elements play a key role also in the field of the electric cars or other important key products to ensure the energetic transition, which is a challenge currently. And of course, in order to see whether the process may be sustainable or not, we applied a life cycle approach. More specifically, so going a bit into the detail of what we have done, we took some wish-shredding dust sample and sent them to a two-stage hydrometallurgical process. The first one was a double-stage sulfuric acid leaching, targeting rare earth elements and base metals, which may still be present, of course, in this dust. The second stage was carried out using with tauria in order to recover precious metals. Both the wish-shredding dust, the leachates obtained out of the two leaching stages, as well as the final solid residues, were analyzed and characterized in terms of metals, both base and precious, as well as in terms of rare earth elements, in order to see how much of these elements, of these valuable materials, we could extract with this approach. And these are our results, the results from the extraction yields. As you can see, most of the rare earth elements, which are here highlighted in green, were mobilized, extracted. Of course, the extraction percentage varies from a minimum of 9 to up to 99%, and this, of course, depends on the form in which the rare earth element is present, because this influences its capacity to be extracted, to be leached by sulfuric acids. Also, base metals were basically mobilized, with the exception of lead, which usually tend to precipitate as sulfate. Interestingly, we found also some extraction of gold, which is actually not expected, but there are some evidence in literature that support these results. In the second extraction stage, which was the one targeting the precious metals, we mobilized almost all the silver that was present in our dust, and another good, I would say pretty good amount of gold. But as you can see, also some base metals and rare earth elements, which were not expected to be leached out, were found in our Thiourea leachate. And this is probably due to the presence of some residual sulfuric acid from the first stages that may have influenced and driven these results, basically. Now, although the results that I've shown, especially if compared with literature, are quite promising, our concern was on the sustainability of the process. And I will now leave the floor to Michela, who will tell you about the life cycle approach that we implemented to check this aspect. Thank you.
Okay, can you see my screen? I hope. And the presentation
Yes.
too? Yeah, perfect.
Fantastic.
Okay, perfect. So, as introduced by my colleague Alessandra, one of the most significant questions was, is this process sustainable, and under which conditions can be considered sustainable? Because when we are talking about circular economy or closing the loops, we know that sometimes the best option is not always try to recycle. In some cases, the potential impact of a recycling process can be higher than the production or extraction of a new raw material. So the question is, the process is promising, is potentially promising, but we have to assess if it's sustainable too. So for the reason, we applied the life cycle assessment methodology. I suppose that you know what is the life cycle assessment. In the slide that you can see the general definition provided by the CETAC Society. So it's an objective procedure for assessing energy and environmental loads related to a process, but also to a product or a services. So it's an inventory of all the input in terms of energy and material, starting from the extraction of the raw material through the transportation, the manufacturing, the assembling, distribution, the use phase, reuse, recycling, and the final disposal. More synthetic definition is provided by the ISO standard, in particular the 14030. So life cycle assessment is a compilation and evaluation through the entire, the whole life cycle in terms of input and output flows, as well as the potential environmental impacts of a product system. So we applied the life cycle assessment methodology to this process of a recovery, and using as a reference of the ISO standard, in particular the 14030 and 44, and the product category rules that is registered in the International Environmental Product Declaration System, that is called Solid Waste Collection, Treatment, and Disposal Services, was registered in 2022 and developed by the authors of this paper themselves. In the slide, you can find some of the main hypotheses of application of this LCA. So the functional unit was set in 1 kilogram of waste of electrical and electronic equipment processed. Generation in terms of generated dust is considered about 2% in mass. For example, an average distance of 200 kilometers was supposed in terms of transport from the point of waste collection to the facility where we process this material. And in this slide, you can find the main, of course, main system boundaries that was considered in the system. So starting from waste collection and all the processing steps till the final disposal of receipts. In the definition of potential result, environmental results, we use the most common environmental categories used in the life cycle assessment, which are the global warming potential, eutrophication, the acidification, the photochemical oxidation, and the water scarcity index. And we added 2 further categories related to toxicity, in particular human and ecotoxicity, and a set of 5 different characterization model was used for the evaluation of resources consumption in terms of abiotic depletion, because the final results depending, in this case, strongly from the type of characterization model used for the analysis. In the slide, you can find some results that are shown in our paper. As you can see by analyzing this figure, you can see that the main environmental impacts of this process is the leaching steps, and in particular the second leaching steps. So in the figure you can find in yellow, and while the first step is in gray. So both these leaching step have a contribution of more than 90% in almost all the environmental impact categories. So in the acidification, in eutrophication, in the global warming, in the photochemical oxidation, and so on. On the other hand, if we look at the assessment and the result concerning the resource depletion, we have a variation that are between 75 and 95%, depending on the type of characterization model used. Are the last histograms on the right, and the residual contribution in this case to the whole impact is due also to the rare earth elements, precipitation, and to the base metal management of the receipts of the base metal in terms of end of life that you can find in red in the figure. While we have this high contribution to the impact due to the reagents, we know that the use of hydrogen peroxide in the hydrometallurgical processes generally is always impacting in all the life cycle analysis we performed also in the past. In this case, it's not so significant because the quantity used in the step 1 is not so significant. It's a limited quantity used, and so this is the reason we have this great contribution of a second step of leaching due mainly to the use of thiourea in the process for the extraction. Further step of this life cycle assessment was the definition of 4 different scenarios. They differ for the type of allocation criteria in mass, and an economic criteria, allocation criteria was used too, and the potential recovery of the base metal. So we define 4 potential different scenarios considering mass allocation or economic allocation with or without base metal recovery. For the economic allocation was used the average metal price for 2021 defined by the United States Geological Surveys. And in all the 4 scenarios, what we found, and this is important, probably one of the most significant result of our research, is that the resource recovery from this shredding dust and the leaching process for recovery, the primary, for recovering the base metal and the rare earth elements, and in particularly the precious metal like gold and silver, is less impacting than the extraction of the primary metals. So this process is more sustainable. This is an important resource, of course. If we consider the case of rare earth elements in particular, we found a different result depending on the type of scenario, of the considered scenario. So in particular, for scenarios 1 and 2, so without a base metal recovery, we have a small opportunity and a smaller performance in terms of efficiency, environmental efficiency, I mean environmental performance, because just in a few categories we have a real environmental benefits, in particular in the eutrophication and human toxicity. If we consider the scenarios 3 and 4, so where also a base metal recovery is considered, beside the recovery of the precious metal and the rare earth elements, the environmental benefit is higher and considerable for more impact categories. So not only for eutrophication, but also for global warming potential, for the human and the ecotoxicity in general. So we have, of course, a better performance. Some conclusive remarks from analyzing the process in general. What we can say as a conclusion, and in our opinion, these are significant conclusion. This process of wheat shredding dust applied to the wheat shredding dust is a good and potential good candidate material to supply some critical elements that can replace the extraction of primary resource. The hydrometallurgical approach seems effective, in particular for the rare earth elements, because we have an extraction yield that in some cases is up to 99%. And if we consider a mass flow analysis, we see that the recovery yields, of course, depending on the type of elements, have a strong variation, but it's quite good for many elements because it varies from 77% to 84%. Of course, further efforts are needed to improve mechanical selection effectiveness, and in particular, we observe the need to reduce the competition between the recovery of rare earth elements and the base metal recovery, because they are potentially competitors during the leaching process. And the feasibility of gold and silver recovery is still critical due to the high impact of the reagents. As we stated through the life cycle assessment analysis, the impact of the reagents used is the main contribution to all the impact categories. So, of course, this is a not spot and a critical point that at industrial scale up needs to be managed. In terms of life cycle assessment results, we can conclude that, as said, the main impact in all the environmental categories is due to the use of chemical, the sulfuric acid, the hydrogen peroxide, and in particular the thiourea. The advantage in terms of environmental impact is quite evident in most of environmental category. So we can conclude that this process of resource recovery is more convenient from an environmental point of view than the primary production or the primary extraction of the metals, in particular if we look at gold and silver, so to the precious metals, of course, independently from the characterization model applied. If we look on the other end to the recovery of rare earth elements, we found that the scenario 4 is the most promising, with lower impact if compared to the primary production of the same rare earth element. Of course, these promising results can be increased with an industrial scale-up of a process, and in particular, in this scale-up, we need to pay more attention to the use of chemicals and to the use of reagents, the leaching processes, and in particular, of course, we can reduce the quantity at industrial scale-up, quantity of reagents used, but we also can consider the substitution of some reagents with other that are less impacting. So, for example, the substitution of hydrogen peroxide with alternative oxidizing agents with a minor environmental impact. So these are the main results. I thank you for your attention and for this opportunity to present our paper and our main results. And of course, we are here for any question, and thank you again for your attention.
Thank you so much, Alessandra and Michela, for that very interesting presentation. I know that I definitely enjoyed it. So I will start things off just by noting to our audience that the floor is open for questions. If you have any questions, please feel very free to post them in the Q&A now. We actually already have a question in there. It has been answered, but I like to go through the questions because for the archived version of this recording, there will be no chat. So there was a question: what is the difference between the REEs and the precious metals, or in terms of what the definition of these? What are they for your presentation? And actually, it was actually already covered on the following slide. I think that the precious metals were gold and silver, and the rare earth elements were quite a number there. But thank you for that. Thank you for that question anyway. So just to, as a formal record that question was asked. So if you have any further questions, feel free to post them now. In the meantime, while we give people the chance to put their thinking caps on, I have a couple of questions of my own, or rather discussion points, I would say. I was quite interested in this. So obviously we have lots of different recycling industries, you know, plastics and paper and also the waste electronics, etc. And it struck me that out of the recycling industries that we have, this would have to be surely one of the most heterogeneous waste streams that you would find. You know, in plastic recycling, yes, you have contaminants, you know, food residue, oils, etc., and different types of plastics. And of course, in paper, you also have some contaminations and things like that. But I suppose with waste electronics, you often have many different components. These are very complicated devices that we're talking about: phones, appliances, printers, whatever. So I was just wondering if you wanted to perhaps talk a little bit briefly first about how hard this waste electronic equipment management is compared to other types of waste management, sort of the key challenges in the recovery and recycling of these materials, and what makes them different from other waste streams.
Maybe I can start on this point, and Michela can add something. I think that you got the main point. The heterogeneous composition is for sure the hardest point to deal with. But I have to say that when going to recycling or even earlier, when you collect this kind of waste, you try to do it by category. So you try to group different devices according to their main characteristics. Of course, you may have I don't know, a fridge and an air conditioner, which are completely different devices that may be grouped together for a number of reasons. Practical, technical, mainly of technical-economic feasibility of the overall management. But it is very difficult that you will find someone using the same management or I would say treatment line to process a fridge and a mobile phone, for instance. Okay, so this is something that is usually done. And which shredding dust we focus on, for instance, belonged from mechanical treatment plant processing small electronic devices and IT equipment. So this is the reason why we found a lot of rare earth elements, because mobile phones, for instance, are almost full of this kind of materials. So
You've made me very interested now. Perhaps you have an example of a grouping and why they are grouped the way they are?
As I said, the grouping depends on the overall characteristics. For instance, in Italy, the management of WE is regulated, is disciplined by an European directive, which is then specifically applied considering the gathering of waste electrical and electronic equipment into 5 different groups, which are the so-called large whites, so fridges, air conditioning, and so on, the cooling equipment, which are this one, larger other, for instance, washing machines. Okay, then you have the lighting equipment, all the lamps, light sources. The small, as I said, electronic devices and information and technologies, electronic equipment. And the last one should be, let me think, I do not remember the last one, actually.
That's okay.
Yeah.
Very interesting. I find it very interesting.
I want to just to add some consideration. It's quite good, your comparison between the plastic recovery and the WE recovery, because it's a multi-material recovery. So when we talk about paper, is paper, more or less paper. Glass is glass, but we have also difference in type of glass, in type of colors. So generally, it's always a multi-material. But for plastic and for WEs are a critical point. But there is a difference, in my opinion, because when we are talking about plastic, it's a multi-material with different polymers. And the problem of plastic is that when you recycling this material, not all material have a good value from an economical point of view or are requested by the market, or in many cases, the material that you recover can produce other object or not the same object for the primary use of a plastic. So it depends on the thermosetting characteristic of the type of polymers and so on. So they lose value recycling after recycling. Generally, is this one of the main problem of a plastic recycling, and not only not the only one problem, or one of the main problem. When we are talking about the we and the recovery and the type of process we propose in this research, we recover elements. So silver, gold, and this is important because they are elements, so they are requested, they are a real value, and they can be applied not only for the primary user, so for example, for produce new devices, for new electronic and electrical devices, but also for other purposes. So for example, the energy sector and the electric car. So in some cases, they have an increased value also after the recycling process. Plastic generally lose value, from an economic point of view, I mean.
It's actually wonderful that you've brought this up, Michela, because that actually was about to be my next question. I was really curious. What kind of purity you were able to achieve with your recycling, whether you have issues with contaminants, whether you have issues with downcycling, which you've just spoken about, and also about the economic viability of recycling of this waste electronics as opposed to, for example, plastic, which often struggles with economic viability. Maybe you've more or less talked about some of that now already, but maybe you could touch on the purity of the materials that you are recovering?
No, we do not have data on the purity because actually we just extracted this material from the solid waste. Once brought into leachate, you can then apply other techniques to effectively recover them, okay? And bring them into a form that, as Michela said, have the highest possible economic value. So at the moment, we have this kind of data. We just measure the concentration of the target elements. But this opens to another point of these processes in recovery, which is the selectivity. Now it's more and more important to design and set up recycling processes that are as selective as possible in order to take from your material just, or at least primarily, what has the highest value, and then the rest if it makes sense.
Indeed. This is very interesting, and you've covered anyway more or less what I want to talk about. I'm just looking at the questions that are currently coming in, and some of them are kind of linked to what I was about to ask you next. So what I'll do is I'll start with one question from the audience, and then I'll add something that I wanted to ask you onto it that's related. So we have a question here. Is using chemicals in the chemical recycling process safe for environmental sustainability? Now, I know that you had a look in your LCA and you said that these leaching agents were a large portion of the LCA issues. So that was the question from the audience member, but I also would like to tack onto that question whether perhaps it wasn't clear to me whether these chemicals that are used for this leaching are recovered and recycled or not. And also whether perhaps there are alternatives to leaching that would be more environmentally friendly, for example. And so just a set of related questions there for you.
Yeah.
No, in the life cycle analysis, in this life cycle assessment was not considered the recovery of regions, was not considered. It's possible, but one of the main results is that the process is more sustainable than the primary production of this metal, also in case we have no regeneration of the regions. So
that's actually quite an important finding, because it would mean that it's already in line, and then if you were to improve it by recovering and recycling the reagents, then you would actually be even better.
What we expect at scale-up level, we can, for the same yield, a reduction in terms of consumption of reagents. But if you wanted to add some more aspect, Alessandra, I leave to you.
Just about the alternatives. For sure, there are alternatives. For instance, there are a lot of studies with promising results that use bioleaching processes. So these processes basically use the ability of some microorganisms to leach out from the solid waste target elements. From an environmental point of view, it may be more sustainable, but microorganisms action is usually lasts longer than chemical reactions, and this must be taken into account when you propose a new process. Also, the waste you want to use has an heterogeneous composition, and sometimes some metals which are present in the wheat can be toxic to metals. So these are the main aspects, the main reasons why bioleaching has not developed that much. More recently, there's also attention on alternative chemicals such as organic acids that can be obtained, first of all, out of waste material, for instance, from the anaerobic fermentation of organic waste. So you can use the output of a waste recovery process to recover other valuable elements from waste, or dipiothetic solvents, switchable solvents. There are really a wide variety, which is under study, let's say.
Very nice. Sorry, I'm just looking again at the questions. So I'm not going to ask any of my questions anymore, because we have a few more here and we've already sort of come a fair way in the question time. We have another question here. Can the REEs be concentrated in some size fractions of the dust rather than other sizes? So whether there's concentrations of rare earth elements in various fractions of the dusts in terms of size.
In a previous work that I carried out, we performed a granulometric analysis of the dust, and we characterized the different fraction to see if there was any difference. And usually the finest fraction is the richest.
Okay, and what sort of differences? Is it large, very large differences between the fractions, or?
I would not say very large, also because you have to consider that these are trace elements, so the initial concentration is not that high. So.
Very nice. The next question, also from the same audience member. Which methods do you think are most promising in relation to separating the REEs to usable forms from your solutions?
As I said, this is a very complicated question to answer, because in order to identify a process as promising, you need to take into account, and as promising in view of a scale up, so in the view of applying really that process, you need to take into account a lot of aspects. the process must be effective, must be sustainable from an environmental point of view. But as Michela pointed out, answering one of the first questions, you should also take into account the economic value of what you need to take out. And the economic value has somehow to counterbalance the costs of the treatment. So it's very difficult to say, especially when, as I just mentioned, a lot of options are being studied currently.
Yes, one of the points that we outlined in the presentation, a potential further research is to reduce the competition between the extraction of a base metal that has a lower economic value and the rare earth element. So if you move to a higher yield in terms of recovery of a rare earth element, you have a more promising process. But you have to investigate, of course, a potential solution or different regions, for example, or different process condition.
And the final question, which I actually think Alessandra may have already sort of covered, but maybe you have something that you want to add. Is it possible to use green solvents and chemicals to replace conventional ones? I know you talked a little bit about the microbiological alternatives, but maybe there is something you want to add.
Pardon, I didn't get it very well. It is possible?
Is it possible to use green solvents and chemicals to replace the conventional ones that are being used in this process?
Yes, yes, of course, you can replace sulfuric acid, thiourea with greener solvents. This is the address that LCA results gave us, and actually the direction that our research has just taken.
Wonderful. Okay, well, that's the end of the questions there. And given that we're already at the 1 hour mark, I won't read any more from my list. I want to thank Michela and Alessandra so much for being with us today. I think I really enjoyed the presentation, and I get the feeling that the audience also did. Oh, we got a little clap reaction there. So thank you so much, both of you for coming and for your wonderful presentation. I'm going to now share my screen again, just to provide the closing address. So the next presenter will be Nils Hanne Klaus from the University for Continuing Education, Krems in Austria. He's also going to talk to us about rare earth elements, but in this case, rare earth elements and uranium in phosphate fertilizer products. That presentation is going to be on Thursday, February the 13th, 2025 at 10 a.m. Pacific time. So be sure to join us for that if you are interested in that topic. Okay. So that's all from me today. A big thank you again to Michela and Alessandra, especially given that they're sick. So thank you so much for coming. And thank you for all of our audience that joined us today. Hope to see you next time. Goodbye.
Goodbye. Thank you, Mitchell, again for this opportunity. Thank you very much.
My pleasure. Thank you.
Bye. Thank you.